Hey everyone, so we're going to talk a little bit more about circuits today. We're going to kind of review stuff we've done in previous classes, um, but we're going to look at a way to make it a little bit easier for you. So just a quick reminder, series circuits, current is the same everywhere, voltage adds up to be the voltage of the battery, and the resistance is to get the total resistance or equivalent resistance, you just add up all the resistors. Parallel, a bit different. In parallel, the voltage is the same everywhere. The currents add up to the total current, and to get the resistance, the equivalent resistance, it's actually a little bit different. It's this 1 over equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. We'll make sure we spend a little bit of extra time going over that because a number of you did miss that one on the Google form from last time. All right, so we have a series circuit here. So it says, what is the equivalent resistance for the circuit to the right? So we know in series, we just add them all up. So let's see. So R equivalent equals, I think it was 4 and 5, right? Yeah, so 4 ohms plus 5 ohms, 9 ohms. All right. Just get in the habit of, I know you guys can all do that in your head, but why don't you just write it out? Take the extra minute just so you get in that habit of not mixing up our equivalents. The next one says, what is the current through each resistor? So one thing to remember is that the current is the same everywhere in a series circuit. I would write that down right here. The current is the same everywhere in the series circuit. So if you get it in one place, you get it everywhere. Okay? So a lot of people might get stuck here and say, I don't know, there's no current values anywhere. I don't know what to do here. But what you can always do to find the total current through the system, or the equivalent current, whatever you want to call it, you can use the equivalent resistance and you can use the battery. So I'm going to say I, and I'm going to call it total. Some people call it I equivalent. We could do that too. We'll call it I equivalent equals V equivalent, or V of the battery, over, I'm going to write that V battery, over the equivalent resistance. All right? So I equals the voltage of the battery is 9 volts. The equivalent resistance is 9 ohms. I don't know what that was. So we get 1 amp. So that's the total current, but that's also the current everywhere now. Okay, so 1 amp. So let's start labeling stuff. All right, the current here is 1 amp. The current here is 1 amp. The current here is also 1 amp. What you can also say is the resistance here through the battery, even though the battery doesn't have a resistance per se, the total resistance of the circuit you can put there too. So you can put the 9 ohms there. Does the battery have 9 ohms of resistance? Absolutely not. Don't tell me that it has any resistance. But sometimes people like to put the total resistance or the equivalent resistance by the battery just to keep track of it, to put it somewhere. All right, what is the voltage drop or potential difference across each resistor? Okay, so here's how you do that. Look at each resistor. Each resistor has a current and a resistance. So if you use the equation V equals IR, using the current for that resistor and the resistance for that resistor, you can get the voltage. Okay, for example, this one here, we'll call this V4 because that's the 4 ohm resistor. We have 1 amp and 4 ohms. So we have V4 equals 4 volts. Okay, it's just a coincidence that the voltage is the same as the resistance. The reason being because the current is 1. So V5 would be the current going through resistor 5 and the resistance of resistor 5. So V5 equals 1 amp times 5 ohms, and V5 equals 5 volts. Again, just a resistor that just a coincidence that the 5 ohm resistor has 5 volts. All right, so here's what I'm going to do. I'm just going to take these and I'm just going to bring the work for them down. Copy. I'm going to paste that there. Copy. I'm going to paste that there. All right. So the voltage of resistor 4 is 4 volts. The voltage of resistor 5 is 5 volts. Okay, now we got to think to ourselves, do these agree with your series equations? Well, the first equation for series is that all the currents are equal. Are all the currents equal here? Yes. I equals I1 plus I2 plus I3, etc. Okay, I said equals, but I wrote plus. Okay, and we have that here. All currents are equal, so that checks. Okay, maybe if you wanted to write this differently, maybe it would be better to write it like this. Instead of writing I1, since we called it I4 and I5, you could say I equals I4 plus, or equals I5, etc. Okay, so that checks out. They're all 1. Now, how about our voltages? Remember, the voltages add up. So our total voltage through the battery equals the voltage through the 4 ohm resistor plus the voltage through the 5 ohm resistor. Does that work? Well, this one, the voltage of the battery is 9 volts. Voltage of the 4 ohm resistor is 4 volts. Voltage of the 5 ohm resistor is 5 volts. So yeah, that checks off as well. All right. So maybe take a second, just go back, think about what we just did, and see if you can at least think through it on your own. You know, this is a little bit new to us because before we haven't really been calculating a lot of values to find the voltage before, or to find the total current before. All right. So now we're going to look at a much easier way to do this problem, or at least a way that's easier to stay organized. All right. We're going to use this thing called a VIR table. I'll show you how it works. It makes your life so much easier. Honestly, the hardest part of this question is going to be on like a quiz or something. If I don't give you the VIR table, you have to write it from scratch or like know how to make your VIR table. That's usually what people find the hardest, but that's really not that hard. So let's see, we have a 12-volt battery connected to 3 light bulbs in series with different resistances. Determine the current in the circuit and the potential difference across each resistor. Does it add up to 15 volts? Meaning, like, do the potential differences add up to... Actually, I changed something there. It should be, does it add up to 12 volts? But you don't have to think about that question yet. So first, let's just draw this circuit. So here's my battery. All right, so I have my 15 ohm resistor, my 20 ohm resistor, my 25 ohm resistor, and my battery. My battery has a voltage of 12 volts. Over here we have 15 ohms. Here we have 20 ohms. And here we have 25 ohms. So here's what the VIR table is for. It's for basically keeping your data organized. For example, we have 4 givens already. Where can I put those? Well, let's start labeling them. This is 15 ohms. I'm going to put the ohms up here so we don't have to put in each box. This is 20 ohms. This is 25 ohms. It's just listing my givens. It looks like the voltage of the battery is 12 volts. So where am I going to put that? I'm going to put the voltage of the battery down by R equivalent. Okay? Because we know the voltage across each of those resistors is going to be a little different. Now in a series circuit, we know that current is the same everywhere. I don't know why I put a 2 there. I meant to put an A. So we know that current, same everywhere. That's just good to know. But we haven't gotten the current yet. All right, so what can we do here? What do we know? So one piece of advice I'm going to give you is that in any given row or column, if you have 3 unknown, or if you're only missing 1 unknown, or if you only have 1 unknown rather, you can find that unknown. So looking at all the rows, every row has 2 unknowns right now, so I can't solve in a row. But looking at the columns, it looks like this last column here only has 1 unknown. Okay, how do I get that unknown? So I'm going to put, my givens are in black, I'm going to put the values that I find in blue. So I can find the equivalent resistance, can't I? 15 plus 20 plus 25 is going to be 60 ohms. Okay, so that's the first step. That's the first thing I did, find the equivalent resistance. You might want to show your work for that, right? R equivalent equals 15 plus 20 plus 25. All right, now remember what I just said. If you have 2 givens in any row, or excuse me, if you're only missing, I guess in this case in any row, but if you're only missing 1 value, or if you only have 1 unknown in a given row or column, you can find the other one. So look now, it looks like right here we can solve for what this value is, the current there. So that's step 2. Okay, every time it's going to be a little different. So let's see, I is equal to V over R. That's 12 over 60. 12 over 60 is 1 over 5, which is 0.2 amps. All right. So that's the total current through the circuit. Guess what? What do we know about the current? It's the same everywhere. So this value just goes all the way through. So we've only done two things so far. Now remember, if you only have one unknown in a given row or column, you can solve for it. And we can do that now. Notice how we don't know any of the voltages, but remember, V equals IR. So this is going to be step 3. And I'm going to label these all step 3 because we're going to do these all at once. So V equals I times R, right? That's Ohm's law. So I times R here is going to be, I think that's 3, but let me just get a calculator out. Yeah, so this one's 3 volts. So the 15 ohm resistor uses 3 volts. Now, if we multiply the next column, that's going to be 4 volts. And the last, that's going to be 5 volts. Do those add up to be 12? Let's see. 3 plus 4 is 7. 7 plus 5 is 12. So yeah, that works out. So that works out actually pretty nice. It's a nice check for us. All right. So I like to put the values in. Let's just kind of draw everything going on here. So current's going around this way. Okay. The 15 ohm resistor has 0.2 amps and 3 volts. The 20 ohm resistor has 0.2 amps and 4 volts. And the 25 ohm resistor has 0.2 amps and 5 volts. The reason I'm doing this step here and writing them all in is because you're never going to be asked on a test, fill in a VIR table. You fill in the VIR table and then you tell them the values they want. They might say, what's the current through resistor 1? They might say, what's the voltage across the second resistor? So just make sure that, you know, you take this and then take an extra minute just to fill in these values over here. All right, like I said, you could put 60 ohms here. Again, the resistance of the battery is not 60 ohms. The equivalent resistance, the total resistance, is 60 ohms. So be careful in putting that there. Just keep that in mind. Maybe it's a bad idea to put that there. I don't want to confuse you guys. Maybe it was a bad idea to put it here too. Okay. So why don't you pause the video, try this one on your own, and then unpause the video. All right. All right, so hopefully you tried this on your own. Let's put in our givens first. So our resistances, remember this is in ohms. Ohms, oh, I'm on the eraser, that's why it's not working. This is in ohms, this is in amps, this is in volts. Okay, volts. Okay, so this is 25, this is 25, this is 25, and our voltage here is 10 volts. All right, again, we don't need the voltage there. All right. So what's the first thing you do? Just like last time, basically the same steps, just because of the way this one was given. Let's solve for the equivalent resistance. So in a series circuit, how do you get the equivalent resistance? You add them all up. 75. All right. So now, well, let's see. Can we get the current? Yeah, we can get the current. Okay, so this was our first step. So now we can get the current. Let's see. I equals V over R. So our voltage is 10. And our resistance is 25. Or 75 rather, and we get 0.13 repeating. Now, since it's repeating, we're going to get a little bit of, I don't know the word, what I want to say is, estimation. So when we add them up to check our work, it might not work out perfectly. All right. Now the next one, we have to get our voltages, right? So V equals I times R. If you're forgetting what Ohm's law is, remember, it's R equals V over I, but you can rearrange it to be I equals V over R, or V equals I times R, okay? So let's go through and get all of these voltages. So this is 3.3 repeating. This is 3.3 repeating. This is 3.3 repeating, okay, because this was repeating. So do those all add up to be 10? 3.3 plus 3.3 plus 3.3, yeah, it does add up to be 10, all right? So our work checks out. But again, take this now and think for yourself. Think for a second, okay, what do these values mean? Where do they appear on the circuit? So our current is going to be 0.13 amps. And our voltage across each one is going to be 3.3 volts. All right. And that's all it asks as far as says find the reading of the voltmeter and ammeter. Notice I didn't even read the second half of the question. I just knew to go to a VIR table right away. They're really useful. Sometimes you do more work than you really need to, but I think it's just good to do. All right, it's good practice. All right. So it's just a concept question. If this circuit represents a string of lights, so picture like each one of these resistors is a light bulb, like picture each one was a light bulb. What would happen if one burnt out? So if one light bulb burns out, okay, let's say it burns out, there is a hole in the circuit there. The circuit is now open. Can current go around and get through if there's a gap there? No. So can we light up the other light bulbs? No, we can't. Now, you might be saying to yourself, well, what if one of the other ones was burnt out? Let's say it was this one. What if this was burnt out? Same deal. If you don't have a closed loop, you can't get current going. The current just, no circuit is going to be formed. There has to be a consistent connection or an unbroken connection from one end of the battery to the other. If that unbroken connection does not exist, then current can't get through. Okay, and none of them light up. Now you might be saying, well, can some of the current go through the voltmeters here? No, voltmeters do not let any current through at all. So what would happen if one burned out? They all burn out. Or, excuse me, not that they all burn out. I should say none of them turn on. That's a better way to put it. Now, they make them a little bit differently now, but back in the day when they had like string lights or like, let's say Christmas lights, if any of you already put those up or for any holiday, when one light bulb went out, they all went out. Okay? The reason being, those were strung in series. Now they kind of do them in parallel, sort of, so that when one burns out, they don't all burn out. Okay? Because that was a pain. If you had one light bulb go out, like one burned out, you didn't necessarily know which one it was. And you'd have to go through and check all the light bulbs to figure out which was the one that was burned out. So that was a big pain. All right? So that's a huge disadvantage of lights that are wired in series, and why not many lights are really wired in series. Okay? So I kind of just mentioned that. Now let's look at parallel circuits. Just pretend for a second that you don't have the values here. I know I gave them to you for current. Just pretend you don't know them. So let's find the equivalent resistance of this circuit. So let's take an extra second to do this. So a parallel circuit, to get the equivalent resistance, it's 1 over R equivalent equals 1 over, in this case, 10, 15, and 30. 10 plus 1 over 15 plus 1 over 30. Now, when you put that in your calculator, it tells us that 1 over R equivalent equals 1/5, or 0.2. Now, that is not your answer. You have to now raise both sides to the -1 power. Just flip it, basically, so that R equivalent is equal to 5. A lot of you forgot to do that on the last time you did it for the Google form. Now, what is the total current through the circuit? I know that it's 6. The picture tells you it's 6, but how can you solve for that on your own? So the current equivalent, the total current, is equal to the voltage through the battery over the equivalent resistance. Voltage through the battery is 30 volts. Equivalent resistance is 5 ohms. So we get 6 amps. So that's where that comes from. Okay, you don't have to be told that that's 6 amps. We could solve for it. What's the voltage across each resistor? Look at our equation. Parallel circuit voltage. It's the same everywhere. So the voltage through the battery is the same as all the other voltages. The voltage through each branch. I don't know why I put 6. It's 30. So it's 30 volts here. 30 volts here. And 30 volts here. Calculate the current through each branch. They should all add up to, remember, the current has to add up in parallel, right? The currents add up to the total current. So our total current is 6, so they should all add up. Yes, I know we have the values here. Just for color coordinating, I'm going to make this black. I know we have the values here, but just pretend you don't know it for a minute and see if you can do it on your own. So the current through the first resistor, the one on the left, let's see, V is 30 and R is 10. So we have 30 volts over 10 ohms, and we have 3 amps. The next one, we have 30 volts and 15 ohms. So that's 2 amps. And the last one, we have 30 volts and 10 ohms. Excuse me. 30 ohms, not 10. So we have 1 amp. A few things here. Yes, these all add up for a total of 6 amps. Perfect. That checks out. But also notice the one with the smallest resistance, the 10 ohm resistor, has the most current going through it. That should be something you expect to see. The 30 ohm resistor has 1 amp going through it, so the biggest resistor has the least current going through it. Now, you can see why using the VIR table is a little bit nicer. This, there's all these steps, and it can be a little bit confusing. So the VIR table, remember what we said, if you have one unknown in any column or row, you can solve for that column or for that unknown. All right, so let's check out this new question. You have 4 resistors, 50, 40, 30, and 20 ohms hooked up to a 120 volt battery. All right, here's a picture of it. We'll just say they're left to right. So this is 50 ohms. This one's 40 ohms. This one's 30 ohms. And this one is 20 ohms. All right, and we'll say the battery's 120 volts. All right, so let's start filling some stuff in. So this is in ohms, this is in amps, this is in volts. So this is just like the last one, almost. We have 50 ohms here, 40, 30, 20, and I think our equivalent resistance for this one comes out to be 140 volts, right? Or ohms, right? You just add them all up? No, that's not what you do. Okay, don't do that. We'll talk about how to do that in a second. This is 120 volts because that's our total voltage. How do you get the equivalent resistance? Remember, it's 1 over R equivalent. So 1 over R equivalent equals 1 over 50 plus 1 over 40 plus 1 over 30 plus 1 over 20. So throw that in your calculator. Let's see what we get. Let's see, 1 over 50 plus 1 over 40 plus 1 over 30 plus 1 over 20. So that comes out to be 0.1283 repeating. All right, or I don't even know, actually I don't think it's repeating. I think it's just 3 threes there. Okay, but we're not done yet. You have to invert that. So raise it to the -1 power. And I'm getting we'll just round a little bit, 7.8. ohms. Let's put that in blue because it's a value that we just solved for. So that's the first thing we did, 7.8 ohms. All right, what else can we do? There's 2 things you could do here. Something we know about the voltage in parallel. What do we know about it? Right, it's the same everywhere. So the 120 volts is through all of these. You can call that step 2 if you want. I'm not even going to give it a step name because we don't have to do any work for that. Now, can we get the current? Yes. Is the current the same through all of them? No. It's only the same in series. So remember, I equals V over R. So this is going to be step number 3. Okay? I equals V over R. So 120 divided by 50 is 2.4. Check that on your calculator. 120 divided by 40 is 3. 120 divided by 30 is 4. 120 divided by 20 is 6. Now, you can do this last one 2 ways, which is kind of cool because you can check your work. The first way you could do it is you could do 120 divided by 7.8. 120 divided by 7.8. It's like 15.4. Or you can just add up all the currents because all the current adds up to the total current. So for this last one, two ways to do it. You can add these all up to get a total of 15.4 amps, or you could do the voltage of 120 divided by the equivalent resistance of 7.8. Get the same answer. Great way to check your work. So if the circuit represents a string of lights, what would happen if one light burned out? So let's just pick one over here. Let's say this light burned out, okay? That path no longer exists. Are there still closed loops here? Yeah, actually. Current can go through this way. Current can still go through this way. Sorry for that bad line there. Current can go through this way. Okay, they don't have to go through resistor B, all right? So what would happen if one light burned out? The others stay on. Now this is much more advantageous, right? Like let's say, you know, in your bathroom, if you have like those little lights over the mirror in your bathroom, like those 4 little lights like a lot of people have, when one light goes out, they all don't go out, okay? Because those are hooked up in parallel. All right, so what's one advantage to lights, parallel circuits? Right there. When one of the things in the circuit breaks, everything else is unaffected. So what you're going to do here, and you're going to turn in a picture of your work for this on the Google form, is you're going to, well, here's a circuit, okay? 100 ohm and a 200 ohm resistor connected in parallel to a 10 volt battery. So draw the circuit. Hopefully you can do that part. No problem. Create your VIR table. So copy the ones that we had. There's only 2 resistors though, so it's a little bit quicker. Show me at least 2 calculations. Show me some sort of math work somewhere. And clearly state which value is the same throughout the circuit. So if it's a parallel circuit, what's the same throughout the circuit? Is it voltage? Is it current? Is it resistance? What is it? All right. We are actually not going to meet for class on Monday. We're actually going to meet for class on Tuesday. This is not going to be due Monday night. This will be due Tuesday night, just to give you guys a little bit of extra time. All right. So if you have any questions, I will actually have extra help tomorrow, Monday, or today, Monday, whatever day you're looking at it, Monday at 3:15 and Tuesday at 3:15. All right. Have a great day, and hopefully I'll see you on Tuesday.